Consider for a moment the very essence of light. It dances, it illuminates, it carries information across the vastness of space. For most of human history, light was something we observed, something we utilized, but rarely something we imagined we could truly command at its most fundamental level. Yet, back in the 17th century, a mind ahead of its time dared to dream precisely that. His name was Christiaan Huygens, a brilliant Dutch physicist, mathematician, and astronomer. In a world just beginning to grasp the complex laws of nature, Huygens conceived of an idea so astonishingly advanced it truly felt like science fiction. He envisioned a method to manipulate light, to bend it, to shape it, to direct its path, not with mirrors or lenses, but with an invisible, almost ethereal, thin electrical surface. Picture the sheer audacity of this thought, to influence light itself, not just its reflection or refraction, but its very trajectory, using a subtle, unseen force. It was a hypothesis born of genius, a whisper from the future, laid out on parchment centuries before the tools to test it even existed. For 400 years, Huygens' elegant theory remained a tantalizing, unfulfilled promise. A beautiful concept, certainly, but one that seemed destined to reside purely in the realm of theoretical physics, perhaps just beyond the grasp of practical application. Until now. Until a new era of scientific ingenuity, armed with unprecedented precision and an understanding of the quantum realm, began to unlock secrets Huygens could only intuit. Today, in the quiet, focused laboratories of Britain's Lancaster University, scientists have not only brought Huygens' incredible vision to life, but they've done so in a way that feels both utterly revolutionary and deeply connected to his original spark of insight. They have found a way to truly command light, to direct its beams with a finesse that would surely have left Huygens in awe. Their journey began by selecting very specific elements, ytterbium and strontium. These are not exotic, unobtainable materials. Rather, their atomic properties make them ideal candidates for the kind of delicate manipulation required. The first and perhaps most crucial step in this extraordinary process involved an almost imaginable feat of engineering and patience, cooling these atoms down to a temperature just a tiny fraction of a degree above absolute zero. To put that into perspective, we're talking about temperatures colder than the deepest reaches of interstellar space. Why go to such extremes? At room temperature, atoms are a chaotic, vibrating mess, constantly colliding and zipping around. But as they approach absolute zero, their motion slows almost to a standstill. They become nearly motionless, predictable, and incredibly susceptible to external influence. In this ultra-cold state, these atoms lose their frantic energy and enter a realm where their quantum properties become more pronounced, more accessible, and crucially, more controllable. Once the atoms were suspended in this profound stillness, the team introduced another marvel of modern science, lasers. But these weren't just any lasers. They were precisely tuned, delicate beams of light themselves, used as microscopic tweezers and paintbrushes. By carefully directing these laser beams onto the ultra-cold atoms, the scientists were able to manipulate them with exquisite precision. They could nudge them, arrange them, and essentially sculpt a precise atomic landscape. And here lies the crux of the discovery. This careful manipulation of the ultra-cold atoms fundamentally altered the way those atoms interacted with other incoming beams of light. Imagine it like this. If ordinary atoms are a turbulent river, sending light scattering in unpredictable ways, these ultra-cold laser-controlled atoms become a perfectly designed series of gates and channels. By controlling the atoms with one set of lasers, the scientists could dictate exactly how a second beam of light would behave as it passed through them. The result was truly remarkable. The researchers found they could direct, reshape, and even slow down beams of light. They could create atomic structures that would act like a thin electrical surface in Huygens' mind, guiding and altering light's path with an unprecedented degree of control. It's a profound echo of that 17th century dream, made real through the meticulous, often painstaking work of 21st century science. The immediate implications of this breakthrough are deeply exciting, particularly for the study of quantum mechanics. Our understanding of the quantum world is still evolving, and the ability to precisely control the interaction between light and matter at such fundamental levels provides an entirely new window into its mysteries. This kind of command over light could pave the way for new quantum sensors, more robust quantum computers, and a deeper understanding of the very fabric of reality. This journey, from a visionary thought in the mind of Christiaan Huygens 4 centuries ago to its stunning realization today in a British laboratory, is a powerful testament to the enduring human spirit of inquiry. It speaks to the persistence of scientific curiosity, the incremental progress of knowledge, and the beauty of seeing ancient theories blossom into modern marvels. It reminds us that sometimes the most audacious ideas simply need time and the right tools to become reality. What an incredible fusion of historical insight and cutting-edge technology! It leaves us to ponder what other ancient dreams might be waiting for the right moment and the right scientific minds to bring them to life. We'd love to hear your thoughts on this incredible discovery. How does it make you feel to see a 400-year-old theory finally fulfilled? Share your comments below, and if you found this story as fascinating as we did, consider subscribing for more journeys into the remarkable world of science and innovation.